Good afternoon, everyone. Thanks for coming out to another edition of NMIH's Virtual Museum. Before we get started, I just want to take a minute to talk about some of the other programs coming up here on the Virtual Museum. Next week, we have two programs that kind of coincide with each other. Our historian, Mike Piersa, is going to be discussing the blast furnaces, which if you've been to the museum and seen the iconic blast furnaces outside, you know how amazing they are, but you might not know how they work. So that talk is going to kind of cover that, and Mike is going to talk about the history behind them, how they evolved, and how they were used to, you know, make product by Bethlehem Steel. And then he'll also be talking about the blowing engine house. If you've been on the Hoover Mesa Trestle at the Steel Stacks campus, you've looked down into that big, huge, kind of amazing building. So you'll be able to learn exactly what those giant engines did and how they powered those blast furnaces. So there's two very good talks that are coming up that Mike's going to be presenting. The first one is on Monday at 2, and the next one is on Wednesday at 2. And we also have several other programs coming up. You can check those out right here on our Facebook page or at NMIH.org, which is our website. We have children's programming that's going to be launching next week, which we're really excited about. And we have online industrial story time tomorrow. So there's a lot of things going on. We have a full schedule of events going out until the end of the month. And if you're tuning in live or watching afterwards, I just want to thank you again for joining us. While the museum's closed, obviously we haven't been able to have patrons in the museum, but we've been, reaching everyone through these great online talks that we've had our historian doing, and we've been bringing in people from all over the world to talk to you all. If you're watching this, you know that it's free, and if you're able to right now, we ask that you try to support the museum. There are several different ways that you can do that. You can find them on our website at NMIH.org, or I'll be pasting a link down in the comments below. A couple of different ways that you can do that are either purchasing a museum membership, donating to the museum, or one thing that you can do, which actually coincides nicely with this talk, is we have a book that Mike authored about the Corliss steam engine that's in the museum. And you can right now buy a copy of that book, and you'll get emailed a link to a digital copy. And then when the museum reopens, we'll send you a physical copy as well. So you get both of them. I believe it's for $18. And again, you can get that on our website, or you can click the link below in the comments. Without further delay, I'd like to bring in Mike. Mike is the museum's historian. He has a bachelor's in history from Moravian College and a master's in history from Lehigh University. He's been with the museum in some capacity for over 17 years. And he's been really instrumental in the research behind what's in the museum and the interpretation of our collection. And one of the most, the largest things that he's worked on is what he's talking about today, which is our Corliss steam engine. It's a 115-ton steam engine that we brought back to operational power under Mike's oversight. So a lot of great history that Mike has worked on, and I'm sure he's very excited to talk to you about the Corliss today. So without further ado, I'm going to pass over to him and enjoy his talk.
Thank you, Glenn. I'm going to begin a screen share so we can actually see a slideshow while I talk. So I'll go through the details about our engine here. So I'll just take a moment to get it set up. And it should load any moment now. So the first image here you're going to see is actually an artist rendering by Alex Carnes showing what our steam engine looks like when it's fully put together, fully restored, and has all of its oiling system on it and running at speed. Shows in its original color scheme as it came from the snow factory in Buffalo, waterworks green, black cylinders, piping, oil system. So when we start looking at steam engines, we want to realize that this thing really wasn't all that unique. It's a very rare survivor today. I'm just trying to get my screen to scroll here. But if you were in Pennsylvania 100 years ago, and you could look up, down, and around, and well, you couldn't really see down too far, but you could find engines pretty much everywhere, up on hillsides, at water level, and even in the coal mines, which is what steam engines were first developed for, pumping water. So I wanted to throw this in there and show that when our engine was built, there were also engines all over the place. This was about 400 feet underground, a similar type of engine, not all that different from ours, pumping water. pumping water for mine drainage, and our engine was pumping water for municipal use. So these things were very common and very important. So if you look at pretty much any facet of daily life that involves water, unless you had a strictly gravity-fed water system, you had to have a pumping engine or water pump at some point in that system to make that operation possible. So our particular engine came from the York Water Company. The York Water Company was established in 1816 as the oldest investor-owned utility in the United States of America. They had an earlier pump house in downtown York. But in 1897, they opened a new pump house on Codorus Creek, a little bit southwest of York. The original pump house was located in a place where a paper mill took up residence nearby. So you can imagine the discharge that came from that. So they decided to move the pump house further outside of town, where they could get a nice clean water supply. And then they could also pump up into a reservoir, 40 million gallons a day, and gravity feed down to the city below them. So this is what the pump house would have looked like down in York. And for those of you who aren't familiar, I know there are a lot of international visitors. York is a little bit north of Baltimore and west of Philadelphia and south of Harrisburg, Pennsylvania. So you see a giant smokestack that was tied in with the boilers. There were usually, depending on the year you visited, about 2 boilers available, and usually 2 or 3 steam-powered pumps. The station that our engine came from was built with 2 Worthington steam-powered pumps. Get there eventually. Here they are. This is a view inside the engine house, pump house, I guess, technically. So what you see here are the predecessors to our pump. These were built in 1897, and each of these pumps put out about 5 million gallons a day of water. You'll notice that there are no flywheels. There is a common piston rod that goes all the way through from the steam side, which is the front of the mechanism, to the water side, which is the back of the mechanism. These are very rare today. I'm only aware of one that actually survives in this country in a decrepit state. And if anybody knows about their survivors, please tell us. But these are triple expansion pumps, no flywheel. They're duplex pumps and also tandem because, again, the pistons are on the same piston rod. And these are also Corliss pumps because they use Corliss valve gear. So what Corliss means is that you have 2 inlet valves at the top of the cylinder and 2 exhaust valves at the bottom of the cylinder. So the easy way of understanding is breaking this side in half and imagining you want to push the piston one direction. So you have steam come in at the top, push the piston, and it exhausts at the bottom. And then you just multiply that to the other side of the cylinder in the mirror image, and then add 2 more cylinders. The big deal about this pump is the steam would actually start near the middle in a very small cylinder you can't even see because it's obscured by the valve mechanism. The steam would be used once, then it would exhaust into a second cylinder, be used again, then it exhausts into a third cylinder. So the steam gets used 3 times. And because you're using it 3 times as opposed to using it once on, say, a typical steam locomotive, it was much more efficient that way. And with the Corliss valve gear, you didn't just throttle the steam, you took the steam at full pressure, and the Corliss valve gear would control it. So the actual valve on top of the cylinder would close, or what they called cut off early, and allow the steam to expand completely sealed inside that cylinder, pushing the piston and using the expansive power of steam, therefore deriving more efficiency and cutting your fuel bill between 30 and 50%. So this was a very efficient machine. But by the time the first couple of decades of the 20th century were reached, the water company was looking to expand. They needed more capacity, and they were looking at what kind of pumps could they use as a more advanced technology. And they started looking at these things and realized you've got 1, 2, 3, 4, 5, 6 steam cylinders on one pump that only pumped 5 million gallons of water a day. What happened in the late 19th century was they developed a technology called a cross-compound horizontal pumping engine. That's what our engine is. So instead of those 6 steam cylinders, we only have 2. So that's 1/3 the mechanical moving parts that you have to worry about. You had a couple more with the crankshaft and flywheel, but the flywheel helps maintain momentum, helps the machine run smoother. And this was laid out in a very logical manner, an H-shaped with a flywheel in the center. You have your steam engine at one end and your water pumps at the other. So you could take your cylinder heads off of each, pull the pistons out, do your maintenance, put it back together, and have very little downtime compared to the monstrosity that you'd have to deal with those Worthington pumps if they broke down. So our engine was built for the York Water Company in 1914 by the Snow Steam Pump Works in Buffalo, New York. For those familiar with steam engines, it's a cross compound, meaning you take the steam and you use it twice. It goes across the engine. Small cylinder is 24 inches by 36 inches. The big cylinder is 54 inches by 36 inches. The first numbers are the diameter, and the second number, the 36, is the length of the stroke. So those pistons travel 36 inches every time the engine moves. They're also connected to these big tie rods. You can see in the middle of the photograph, it's a shiny rod that's going diagonally in parallel with the engine frame. There's another rod that ends, and because it's connected to the crank, that drives the flywheel. But there's a tie rod to the right of that and one out of sight that connect back to a pump, which is just a simple reciprocating plunger pump. It goes back and forth, and there's a bunch of little rubber discs that lift up and allow water into the pump chamber. They spring back down, literally under spring power, and then the water that's in the chamber gets pushed out by the plunger displacing it and gets pumped up into the piping network and eventually travels 300 feet to the top of a mountain where it goes into the reservoir and then gravity feeds to the city below. So you can see the engine was repainted over the years. These photographs were taken by Conrad Milster. Many of you might know him from the Pratt Institute power plant in New York City. He visited this engine in early 1980s and was able to take these photographs. The engine ran in daily service from 1914 to 1956. If you look at the maintenance logs, which the water company was gracious enough to let us look at, you can see that it ran day in and day out for a long period of time. It would go down for periodic maintenance, but it would keep on going. They wouldn't even stop it to oil it. They had a oiling system with the central reservoir and gravity feed set up, and that would allow it to oil around the clock. And then if you had to do things like put grease in the grease fittings on the low pressure cylinder, which you see here, they would do it while the engine was in motion, just like the guys on the ocean liners and Liberty ships would do. They wouldn't stop it unless they absolutely had to. So what's interesting about this engine, one of its big claims to fame, is that after 1956, it was still kept operable. They used it 2 weeks a year, and they had to do that to prove to the insurance company it was a reliable backup pump. And they actually used it as a backup pump when they had brownouts, and then during Hurricane Agnes in 1972. They realized that the pump house was going to get flooded. The engine would actually be submerged underwater. So they also realized that when that happened, the electric pumps, which they had installed, would also be taken out of service, and it would take 5 to 7 days to get the electric pumps running again. But the steam engines could be cleaned up and the boilers fired up within 1 or 2 days. So they got the steam engines running about an hour before water in the reservoir would have run out. It was swirling like water in a toilet bowl. So in 1981, the water company was faced with repairs to the boilers, and being, as they proudly proclaim themselves, frugal York County Dutchmen, they did the math to see if they could keep this operation going and maybe even revive the steam engines on a more regular basis. But the refractory cost for repairing the boilers was too high, so it made more sense economically to go and buy a brand new pump. So they went and purchased a 20 million gallon a day diesel-powered pump, and that replaced our steam engine, which was 8 million gallons a day. Now, when they had these periodic runs to keep the engine in good shape every year and prove it to the insurance company it was a reliable backup, they would invite steam enthusiasts to come and see it. That's how Conrad got to go see it and a lot of other visitors. So they knew in the 1970s that this thing had some historical significance to it. And thankfully, the water company management saw fit to find a new home for the pump. And rough and tumble engineers in Lancaster County stepped up in 1981 to actually receive the pump. They installed it in their steam engine building, but as an all-volunteer organization, volunteers do things like get married, have kids, and jobs that they have to go to. So they got the engine mostly reassembled, but never finished the job. They got it into a coat of primer, but never repainted it, and they never got it hooked up to steam. So fast forward to 2009, they're trying to figure out what do we do with this thing, because they realized it was a project that they weren't going to finish. So they approached us and asked if we would like to have it, because they had other plans for the space and needed to get it out of there. So we said, sure, we'll take it. And a little while later, we began work on disassembling it. This is our friend Rick Rowland, who helped make the connection with the engine. We went down, spent a day coating it with rust preventative, because when we first found out about it, we didn't know exactly when it was going to move. So we figured we'd go down, assess the situation, and start formulating a plan. So you can see him here applying, sorry about the screen, LPS3, which is a cosmoline-like material, and that helped prevent further rust on the engine. We also swept it off. This is a good way of seeing, again, sorry about this, just how massive this engine is. The piston on that side is 54 inches in diameter, 4.5 feet, and that's inside the piston, inside the cylinder. So the actual piece of machinery that consists of the cylinder with the valves and everything is much larger. So you can't even stand next to it and see over it. It's that tall. So as you can see, the engine is in a building with a metal roof. Rough and Tumble was very easy to work with. They actually took the roof off of the building for us, and we were able to drive cranes up next to it and pull the engine out. They also helped us disassemble it. This is one of their volunteers, and you can see he's swinging a sledgehammer, and he's going up against a wrench that goes around the nuts on the flywheel. So we thought this was going to be a fairly straightforward process. You put a big wrench on it, put a big hammer on it, and what could go wrong? Well, the wrench broke. So we had to scramble and borrow a giant wrench, and eventually got those nuts loosened up. And we had to disassemble the engine into several large components. The flywheel was split in half. The engine frames came apart. The low pressure cylinder was split apart, and then the high pressure cylinder and bed plate for its side were lifted together. Those weighed together 45,000 pounds and took up the bulk of one tractor trailer. We required 5 tractor trailers to make the trip up to Bethlehem. We can see them inside number 2 machine shop of the former Bethlehem steel mill. They were stored there temporarily, and in our case, temporarily was about 5.5 years. But when you move big machinery like this, you often don't have a plan for exactly how you're going to use it. You just know that you have to go and rescue it and figure things out as you go. So that's exactly what we did. We brought it up here, and then we worked to figure out how do we actually work this into the museum. We knew it belonged in the museum, but there's a lot of give and take when you figure out where do you actually place this. If anybody has questions, feel free to chime in. They should pop up on my screen. And sorry about the technical difficulties with moving these photographs. I'm doing this on a tablet, so not the best situation, but it usually works. So you can see each flywheel half, one of the flywheel halves here, that's 14 feet in diameter, weighs 11,000 pounds, so the total flywheel weight is 22,000 pounds. The next lift here was about 30,000 pounds. That's one side of the pumping mechanism. There's 2 of these, one on each side of the engine. Now, when we talk about the engine being high pressure and low pressure, you have your incoming steam that's used once and then recycled. And each side of the engine produces the same amount of horsepower. One side is actually larger because the steam pressure comes into lower, steam comes into lower pressure. Therefore, you need a greater volume of it to do the same amount of work. But at the pumping end, they've evened it out, so the pumps get an even power flow to them. And those pumps, you can see the silver part in the middle, that's 17 inches in diameter. And that's a plunger that goes back and forth 3 feet with every stroke. Once we got the engine here, we went back to the York Water Company and tried to learn as much about it as we could. So we were delighted to see that when we got to the pump house, there was a mechanical engineering landmark plaque attached to this device here. which was the sister engine. This is located in the spot where those two triple expansion pumps were once located at. This was built in 1925 by Worthington, probably by the same factory that built our engine, Snow Steam Pump Works in Buffalo, because Snow, 2 years after it was built, because Snow, 2 years after it built the NMIH engine, became part of Worthington. So the Worthington engine is very, very similar to ours, just slightly smaller. This is a 5 million gallon a day engine as opposed to 8 million gallon a day, which was what our museum has. The water company was able to leave this the water company was able to leave this in situ where it has been since 1925. And the bay behind it, behind those arches, is where our engine came from and where the diesel powered pump was installed. The water company did a nice display panel here. It actually shows what the valves inside the pump chambers look like. So we can see these rubber discs, the brass washer, spring, and stem, and there's hundreds of these that the water would flow through and then back up against and then get displaced and pushed up through another set of valves and then into the water main system. So at some point we'll probably open up one of our pump chambers and do a similar look into the interior of the actual pump. This is the spot where our pump stood. Ours was number 3, which is logical because the first 2 of the Worthington triples were probably number 1 and 2. So this is the diesel-powered pump that replaced it. You can see it only takes up a fraction of the floor space compared to the old photos of our engine in service. And we're allowed down in the basement below this, which would have encircled the foundation for our engine. We actually found some of the large wrenches that were probably used with our pumping engine, which would have come in handy when we were taking it apart at rough and tumble. The water company was also very helpful in supplying us drawings of the engine. So this is a sample of many drawings that they supplied of the engine, the foundation. And this one here shows the Corliss valve gear on the low pressure cylinder. Again, the steam comes in from the top, goes through the valve, and you can also see those vertical rods coming down. Those control the dash pots, which help the valve close very quickly. And you can see the trip mechanism on here. I'm not sure how well it's going to come across on a video presentation like this, but in person, we actually demonstrate the valve here on the locomotive, sorry, on the engine, by taking a wooden stick and manually turning off the, or disconnecting the latches and allowing the valves to close really quickly. And you can see this happen when the engine is up to governor speed too. But it's one of those things that makes a whole lot more sense in person, but I'll do my best to try to explain as we keep going through the process here. Now, the drawings we got from the water company for the foundation showed it going all the way down to bedrock. Now, bedrock here, I'm not sure if we actually figured out how deep it was, but we knew we weren't going to dig down to reach it. And we also knew that we weren't going to be pumping 8 million gallons of water a day. So we consulted with engineer Joe Michaels. Many of you who read Practical Machinist, Antique Machinery Forum probably recognize his name. He actually worked with stationary steam engines in South America in the late 20th century, setting them up and getting them running as part of his job with the Skinner Engine Company, because that company was still installing steam engines into the late 20th century. So he gave us some really great advice on the foundation. He specified how big the actual pad should be, which is the widest area you see here, that's 18 inches thick. And then he specified inertia blocks, which are the big masses of concrete that go from the top of the foundation block, sorry, the slab is the more technical term for it, up to the bottom of the engine. Those have to be weighted about 4 or 5 times the weight of the reciprocating mass of the engine. That's just the old rule of thumb, and it's worked very well for us. We can actually run our engine at full speed with a quarter standing on edge on the engine, when the quarter will not fall over or show any, to the bare eye, signs of vibration. Next image is a cross-section of some of the foundation. You can see there's rebar installed with it to help tie it all together and reinforce it. And we should be moving on momentarily to the actual construction work. if I could get my screen to work. Very sorry about that. Almost there. So this is a view inside the museum taken from our overhead crane. You're looking down, and where you see the plywood covering the windows over there, that's pretty much the spot where the steam engine is going to be installed. So this is 2015. We were installing trenches for utilities, sewer, water, and getting ready to make the pit for the engine. Bean Inc. from Easton, who we've worked with a lot over the years, is a great friend of the museum, came in and dug the foundation pit. You can see their backhoe and trucks literally drove right into the building. We encountered a surprise piece of concrete. This building was used by Bethlehem Steel as their electrical repair shop. So over the years, a lot of changes were made that didn't necessarily make it to the final drawings that got passed down to us. So when you dig, you never know what you're going to find. So we had to bust out some concrete from a foundation that had extended out into a curved shape over here. And then we also encountered some soil that didn't quite meet the loads bearing specifications, so they actually lowered a little miniature steamroller in there to compact it. Once the engineers had met all the tests, we were able to get to work with building the foundation. So these are the concrete forms being delivered and prepped for installation in the pit. The rebar mat for the slab. You can see the risers coming up for the rebar where the inertia blocks will rise that support the bed plates of the engine. All of the materials used in this were made in the United States. The first order of business for the concrete was to pour that slab and let it harden enough to the point where we could then build on top of that with the inertia blocks. And the concrete can be seen here being poured. It was from Ron's Concrete, and the actual cement came from Keystone Cement, which was located in Bath, Pennsylvania, about 20 minutes north of the museum. You can see the high pressure side of the engine coming, the high pressure side of the engine's frame, concrete inertia block coming together here. Because of the tremendous forces and weights involved, we had 78 cubic yards of concrete. We really had to brace this heavily and make sure it wasn't going to budge. So the first block was poured, and this was done in January or February of 2016. So we actually had to cover the concrete to help it retain the heat, because the building at that point was unheated, and it was still unheated when we started moving the engine in, which happened in early 2016, about 30 days after the concrete was installed. This is what number 2 machine shop looked like at that point. This used to be the largest industrial building in the world, 1,582 feet long, and hidden down in there, you can just barely see it, are parts for the snow steam pumping engine. This is the foundation as appeared with the engine almost ready to go onto it. We did have to do core drilling for the anchor bolts. This is what our engineer advised. And then they were epoxied into place after the engine was installed. Now you saw the photograph we took before from that overhead crane. Well, that crane is only 10-ton capacity and has been out of service for decades. So to actually do the installation, we took some bids, and we had 2 contractors who submitted bids. One of them was going to use a gantry system, which would require steel plating along the entire floor. And the other one called up their neighbor, which was a concrete installation company for precast concrete. And they said they just got this brand new double nickel boom truck imported from Europe. And it would not only fit inside our building, but it could handle the weight of our engine components, the heaviest of which was about 45,000 pounds. So we drove this in here, positioned it, and then we had a team of rollback trucks going back and forth between our building and the machine shop, which was being used for storage, and move the steam engine parts into place. So you can see a 40,000 pound lift over here with the low pressure cylinder. Despite the capacity of the boom truck, this actually required, this pick was so heavy it had to be sit down and repicked after the truck moved a little bit closer. So this was certainly one of the more interesting moves we've done over the years with the museum. You can see it was positioned down on the high pressure side first, then moved over to the low pressure side. Then positioned into place. And then the final alignment was done after the engine was, after these major components was installed. They used jack to put it into the final exact location and do the precision lineup of it. These are the water pumps coming in. And I really apologize about the screen problems today. So you can see this pump is going to be getting flipped around. This is the side facing us that gets connected to the bed plate of the engine. And they just barely cleared the doorway coming in. We actually removed some of the temporary plywood there, and then the plywood that you see still intact is where an overhead garage door exists in the museum today, so you have a sense of scale. That's Bill Hazard from Rough and Tumble. He came up to help us install the engine and line it up there. He did the same thing on their Cooper gas engine, which is a very comparable engine at Rough and Tumble that they actually operate. That was a pipeline engine pumping natural gas. The bottom half of the flywheel was installed. It was left in the pit, then the engine was aligned around it. And then at a later date, another crane came in and installed the crankshaft and the upper half of the flywheel. Pay attention to this big chunk of metal. This is actually the receiver. This is a large kind of tank-like device that goes in between the high pressure and the low pressure cylinder. This had to be installed before the high pressure cylinder because there was physically no other way to get it in there, given the constraints of the flywheel, low pressure cylinder, and concrete that was already in place. So we talked before about how those anchor bolts had to be drilled in. So the core drill was brought in. They drilled the holes, and you can see how it's being lined up with the bolt holes already cast into the machine there. Now, even though the steam engine was built by Snow Steam Pump Works in Buffalo, they didn't build every single part of it themselves. They weren't a steel mill, so they actually got the steel from outside suppliers. And the one piece that we actually found a roll mark on says Laughlin here, and that means it was rolled by Jones and Laughlin, which had mills in the Pittsburgh area just south of Buffalo. And you can also see some stamping marks on there that help identify the part and its location. And the part that you saw there were keys or wedges that were driven into this big pin. You're seeing the top half of the pin here. The bottom half is already inside the flywheel. And if it looks like the flywheel is cracked, that's because it is. It was intentionally cracked when it was manufactured at the inside and outside rims. The middle of it was left hollow, and that allowed the flywheel to be aligned precisely when it was put back together in the field. And there was hollow on the inside at the very ends for that pin to go in. And the wedge you can see would be driven in from the top. Another one out of sight at the bottom, go through the hole in the pin. And the pin was heated to about 500 degrees Fahrenheit. That way, after the wedges were installed, the pin would shrink and provide an even tighter grip. Because of the weight of the engine and the crane, we weren't able to, we had to install those before we installed the concrete floor of the museum. So after the engine was installed, the floor was poured. And you can see the crew came in and did that job over the course of 2 days, the front half of the building and then the back half. And this is what the engine looked like for a couple of months as work in the building was finished, like the HVAC system, utilities. But once that was done, we had a nice concrete floor to work with, a building with light and heat, and we're actually able to spend a good chunk of the winter coming in and doing work on the engine. So you can see in the next photograph here, one of our volunteers, Don Young, is in here cleaning the engine out. Despite being inside the building with a roof on it, there was still a lot of debris that blew into it. So we literally had to go in and vacuum it out. And I really apologize for this. And you can see parts for the engine spread out along the floor, several pallets worth. Some of them, like the oiling system, we're still working on. We kind of cheated and just used oil cups for the time being. But other parts like cladding for the high pressure cylinder, the dash pots, parts for the valve motion. You can see it spread out, plus the workbenches we use to work on the smaller parts. So one of our board members was gracious enough to purchase and donate an overhead pantry, 8,000 pounds capacity that we were able to use for installing the heavier components of the engine. This is an example of one of those. It's a pin that goes into the crosshead and provides a pivoting point for the connecting rod to work from. The connecting rod goes and turns the crank, which turns the flywheel. Now to install that and the actual driving rods, we had to make sure that the engine was in suitable condition to be turned over. So we actually went in with a borescope and did some imaging. And this is inside the low pressure cylinder. And other than a little bit of organic matter, like maybe some fungus or something, it really looked very, very clean. No causes for concern, no giant rust spots. The water company took very good care of it, and being a rough and tumble, it was indoors. So there was really no major issues inside the cylinder that we had to worry about. So to get them moving, we sprayed a mixture of oil and diesel fuel into them repeatedly to act as a penetrating oil. And then used a 10-ton porta power to jack against it to actually get the engine loosened up. And sure enough, it came loose. Might have to do this presentation over again at some point. Normally it's not this temperamental for me. And I know the Zoom is not responding, so we'll just keep on going and hopefully you all can hear me. There we go. Now we're back at the dash pots. These were brought up onto the bench, cleaned up. You can see as we pull them out of their chambers, there's a little bit of rust, but nothing that was really all that difficult to clean up. We re-lubricated them, put them back in, did a lot of cosmetic work, and then we tackled the actual crankshaft of the engine. You can see here we're going in with wheel pads, cleaning it up, getting it down to bare metal. We did this all the way around the engine. And of course, we cleaned it up before we put the crankshaft in too, but we were extra careful and tried to get it as perfect as we could. And then we had one volunteer, John Rohal here, who spent literally day after day just cleaning up nuts and bolts. Then the late Tom Grabko is seen in this shot as we got ready to install the connecting rod. We had to have the engine in just the right position so everything would line up and it could wriggle its way into the crosshead and onto the crank pin. And after you've probably seen all of the dirt and everything involved with this, we actually unofficially won an award. We found this in a nearby factory that was going out of business and figured it was very appropriate here. But the dirt didn't last too long because we got the engine cleaned off and began painting it. Painted the bottom half of the flywheel first, moved on to the top half and the rest of the engine over a marathon 2-day period. Then a professional painting company came in the following weekend as a volunteer job. I was Zarnis from Bethlehem and did the top coat on it. And we think it came out beautifully. color was matched to the original color on the engine. And then the work for actually getting it running began. Now remember that big receiver that we saw lower down? We didn't know exactly where that thing would go, so we put it on blocks and figured we'd adjust it later once we figured out how everything had to line up. So you can see we're down here with jacks and cribbing and level, getting the thing leveled off and moved around so we can have it lined to just where we need it. And we always knew that we wanted to get the engine running, but we weren't sure exactly how. There were a lot of people who said, put an electric motor on it. That should be simple. But we realized that this thing was meant to run under steam, and there's all sorts of issues associated with electric drives. So we were showing visitors around from Vitalik. They're a company headquartered locally that makes pipe couplings, and they saw that we were interested in getting this thing running under steam. So they said, "Why don't you try our brand new steam couplings? We'd be willing to donate some, so the public can see that these couplings are a viable product, and that they can help bring this piece of history back to life." And we thought that was a fantastic idea, because we don't just want to show people what happened in the past. We want to show them what's going on in the present day. So this was really an ideal way of coupling those two together in a literal sense. Now, before we could install the Vitalik couplings, we did have to go and take into account some antiquated pipe pieces that we no longer had with the engine. Those were some 7-inch flanges and another oddball size. So we actually had to have those custom cut at Hart Mechanical in Percy. They did that as a favor to us. And then Worth & Company welded up pipes of more modern standard diameters that coupled to the Vitalik fittings, and we were able to build off of those and begin the process of getting steam back to this thing. So while that was happening off-site, because these guys came in with modern equipment, did a CAD drawing of the system, and they were able to do the fabrication off-site and just come in really, really easily while the museum was still in operation with minimal invasiveness, and actually install this stuff. But while they were off-site, we had to get to work and doing things like installing the gaskets around the steam bonnets here, putting the packing in, getting the valve gear lined up and adjusted. And you can see that everything didn't quite fit the first time. We discovered one part was on backwards, so we quickly rectified that. But by going part by part and taking our time, we were able to do this without doing any damage to the engine. Finally, the Vitalik fittings arrived. What makes these things unique is they actually have a spring-lined, hope I'm using the right terminology for this, gasket inside them that's steam rated, good for 150 PSI. And they just clamp together very, very quickly with pre-grooved pipe sections. And your assembly happens with no welding, no excessive amount of bolting. And it was really, really an ideal situation for a museum that you want to keep open to the public while heavy work like this is going on. Ward Manufacturing donated reducers that went from the large openings on the low pressure side to the Vitalik pipes. We didn't use the original pipe sizes because, again, we knew we weren't going to be running this under full load. It's just physically impossible since we don't have 8 million gallons of water a day to even pump. So we were able to use, I believe, 8-inch pipe for the intermediate, and then a 4-inch pipe coming in. And you can see Mike from Worth probably standing with his pipe job there. Worked out beautifully, done very, very quickly. And next step after that was coming in with compressed air line. This is Dave from Bean Inc. in Easton. They loaned us a 1250 CFM compressor, parked it outside the building, and piped it up with a 2-inch line. And we were able to get the engine running on compressed air. So in the meantime, we're making plans for running it under steam. We haven't gotten to that point yet, but we're moving in that direction. So a local company, CSI Installation, came in with union insulators and installed insulation on the engine for us and the piping. But one thing we noticed when we did the test run of the engine is it didn't quite run right. And we started diving into this and took things apart. You can see we marked it up in yellow paint here. the yellow shows like where the steam would come in, where it would go out, and where the closure point was on the valve. Because we noticed it was only running on the low pressure cylinder. So we did this markup test and we turned the engine over. We realized that the exhaust valves were never actually closing. They were going from slightly open to wide open. And what we learned was that there were two parts of the steam arms on the opposite side. They looked the same from the outside, but on the inside, they're about 90 degrees off. So we switched those around, and then the engine ran flawlessly. There was a problem that we noticed when it was running with the low pressure cylinder, and even on the high pressure cylinder, is that it made a tremendously loud knock. It sounded like it was going to come apart. What it turns out was happening was in the low pressure cylinder, because you're not running under full load, you have a very small amount of air going into the cylinder. It just started pushing the piston, and then the piston was really moving on force from the flywheel. That created a vacuum inside the low pressure cylinder and allowed the two lower Corliss valves to actually lift up, well, one at a time, whichever one was exposed to the vacuum, and drop down. Even though they only dropped down a fraction of the inch, it created a tremendous boom because it's like having a 54-inch drum right there. And that made a really, really loud noise. The engine sounded like it was going to tear itself apart. So after talking to Bill Hazard and hearing about problems with air compressors, and then reading some 1917 era mechanical text, that was the Facebook of the day. These guys would write to each other in their magazines and say, I have this problem. Then next month, somebody would write in with a solution. And it turns out this is a problem that they had back then, too, under Siemens certain situations. So they offered up various solutions that worked with the steam engine, but at the end of the day, it boiled down to we had to find a way of breaking this vacuum or getting more air in there. And we tried different solutions, and we found the one that worked the best was simply disconnecting the exhaust valves and letting the high pressure side do the work, and then the exhaust side really go along for the ride, low pressure side go along for the ride, and the exhaust valves stay open. We tied the arms up, and we operate the valves manually, just about half a revolution if the engine gets stuck on top dead center with the high pressure side. That's a situation where you have the piston trying to push the connecting rod in a straight line, doesn't have an angle to move the crank on, so it can't have rotary motion, so it won't go anywhere. But because the engine is built with the low pressure side 90 degrees off at the crank, that side, even if the other side is on top dead center, the low pressure side still has an angle on that crank and can start the engine moving. So if we manually close those valves and let pressure build up, the low pressure side can start the engine moving, and then we can, again, open those valves up all the way to break the vacuum, then it runs nice and quiet. People who heard it run the first time versus last time couldn't believe it was the same engine. So this is what the engine looks like in service. We can do some neat things with the museum, like turn the lights down, have the spotlights on it. Shots of the governor in motion. I mean, we could do a whole lecture just on governors and how they work, but that's how you do the speed control for the engine here. And then to do some further testing on the engine, we did what they call a rope brake test. Bruce Babcock, a mechanical engineer from Ohio, came in as a volunteer to set up this rope brake, wrapped it around the flywheel, and actually, by using a come-along, which you can see Bruce operating here, put a load on that brake, and therefore transferred it to the flywheel and was able to actually make the engine do some work, which is something we never thought we would see it do again since we didn't have any water. But this rope brake put about a 30 horsepower load on it. And the only reason we stopped there is because we were getting close to the braking strength of the ropes. And the engine ran flawlessly. And we were actually able to take some indicator card readings on it. And we'll show you a video of that momentarily. So this is the indicator. It's a device that makes a chart of the pressure inside the cylinder and how it corresponds to the stroke. You can see when the Seymour air enters, what pressure it is, how the valve closes and shuts it off and lets the seam expand. And you can really get a good sense of what's going on inside that cylinder and exactly when it happens. And you can also plot that out and develop the horsepower from the engine. This is what the resulting graph would look like. That actually looks really, really good. You see The lower lines are the engine running typically with no load at all. The higher line shows the light load. The air comes in at a constant pressure. The valve closes, and the air keeps on pushing the cylinder. Sorry, keeps on pushing the piston inside the cylinder, and the pressure gets lower and lower than it exhausts. And throughout the process, we were monitoring the temperature. This is an infrared thermometer, 73 degrees. That's pretty much ambient temperature. So the engine is really, really performing well. Sounds great. And we just kept on going with the smaller work that we knew we had to do. We had a gauge on the compressor, so we know the pressure going in. But Bill Endereden came in and calibrated the receiver gauge, which is the most important to us. So we knew what was going on with that low pressure cylinder. And we've since gotten the high pressure gauge working well enough to correspond to the compressor. Now this is what the gauge looks like on the inside. Board-in tube and a little gear mechanism that actually operates the needle there. So Bill cleaned it off, calibrated it with modern equipment. And that's been really helpful as we get the engine going and ensuring that we know it's doing what it's meant to do, when it's supposed to do it, and the pressure it's supposed to do it at. So I'm going to conclude here with a little video of the rope brake test. Hopefully it'll play for you all. And then we can take some questions if anybody has any. Unfortunately, I'm not seeing anything showing up here. So Glenn, if you have a way of showing the YouTube video that NMIH has, that would be fantastic. Hopefully you can provide a link to that. Again, sorry about all of these technical difficulties. Usually it's not this bad, but this is probably a good time to see if we have any questions. Anything from you, Glenn? Any of our visitors?
Yeah, Kathy had asked what the most difficult problem you encountered with moving an installation was.
Ooh, that's a really good question. It was really just a number of smaller problems. Like figuring like how do we get this, I guess the biggest thing was how do you get this done in an economical manner? Because this is one of those situations where it's very easy to really get more people involved than it should be, mismanage it, do things that you don't need to do. But we had a very, very good team working on it, a lot of help from volunteers, and we were able to pull all the pieces together. And they really fell into place so that everything got done maybe a little bit longer than we wanted it to take, but without costing an insane amount of money. And everything got done safely, which is probably the most important part. Cool. And one of the more interesting challenges associated with it is a cracked piece of the engine. When it was moved in 1981, they dropped part of it. We actually had to go in and build a reinforcing plate. So that was a new experience for us, but it was really an informative lesson because we got to see why this thing broke in the first place, issues with the casting, and then figuring out how to reinforce it, getting donations for that, and making it blend in so that unless we tell you about it, you probably wouldn't even notice it was ever repaired.
I also have the rope video up so I can share it with everyone as well.
Fantastic. I think these people would love to see this thing in operation.
Putting this engine on a dynamometer, which is a device to measure horsepower by different data input. This thing behind me is a rope brake. This is how you test a stationary engine. When you hear brake horsepower from engines, that's what they mean, power developed against the brake. If you can get this engine up to full speed, that's great, but with no load on it, it's not actually developing much horsepower. So the brake gives it a load to work against. And then, once you have a load to make it work against, you calculate the horsepower with a really interesting instrument, which is right over there.
It's what's known as an indicator. It consists of a few basic components. There's a rotating drum on which there is a piece of paper that is placed. There's a pen or stylus that is moved by a piston in this chamber. There's a counter spring, just like this one, that sets a fixed great. So 1 inch of travel, in the case we have in here, for 10 pounds of pressure.
It's driven by the engine.
Yes. Between the two motions of this rotating and this traveling up and down, you draw a graphical representation of the boiler, or the pressure in the cylinder, as per the stroke and where exactly it is. And with this you can see what the pressure is, what your valve events are. You can calculate your mean effective pressure, and you can also get a horsepower calculation off of what's under the curve here. So basically you have a method of testing the horsepower mechanically and thermodynamically.
Hope everyone enjoyed that. I don't think we have any more questions, so I just want to thank you again, Mike, for joining us, and for everyone out there that's watching live and is going to be checking this out afterwards. Just a reminder, we have a lot of other great programs coming up through National Museum of Industrial History's virtual museum, and you can see those right here on our Facebook page or at NMIH.org. And if you're interested, Mike also authored a book about the steam engine that he just talked about, and you can purchase that on our website, and we will send you a digital copy of the book, and then once we reopen, we'll send you a physical copy as well. So that's also an option for you to not only help us out right now, but get yourself a nice little piece of historical literature. So thanks again, Mike, for joining us.
You're welcome, and hopefully our visitors, our viewers can come and see us in person sometime and watch and experience this engine in person. I think it's one of those things you have to see it right in front of you. It's hard to believe how smooth and quiet it is, and how it actually feels like it's coming to life when you open that throttle up and get a sense of that steam or air flowing into it.
Definitely, I totally agree. It's kind of an amazing thing to see in person. And if you haven't already, please like us on Facebook. And as soon as we are able to reopen, we'll be posting some dates of days that we'll be running the engine. So keep checking back for those dates once we reopen. And have a good afternoon, Mike.